Why Can't I Dance in the Mall? Learning to Mitigate Scene Bias in Action Recognition. And so I'm the presenter, Nick Califano. So we'll start. The motivation for this paper is we'll ask, so what is the action being performed by the person blocked in this video? So there's a person behind this square here. What is the action being performed? So from the scene, we can infer that it's probably some type of baseball task because it's in a baseball stadium. And so the only baseball class in the UCF 101 is baseball pitch. So we can probably guess that it's baseball pitch. However, the answer here was actually singing. So and this is kind of what the authors noticed, that by looking at the background, the model tends to misclassify because it's focusing on its attention on the scene rather than on the human. And so to perform action recognition, you need to be able to look at the human. Scene ends have been shown to perform well on a variety of action recognition data sets and action understanding tasks. So there's kinetics, UCF 101, human motion database. But unfortunately, these models don't always focus on the human, which can lead to poor generalization to the same task in a new setting and poor generalization to other human-related tasks. So if we look at this image here, the bright portions on the bottom half refer to where the model's attention is. So the brighter the portion, the more emphasis the model is placing on those locations. And so in this example, it's not even focusing on the human, it's looking at the floor. And so even though they're doing what looks like soccer, it's looking at the floor, and it would infer that they're doing some type of basketball task. This is called representation bias. So this is a bias of the background related to the class being the class of the action. So for instance, typically soccer is performed in some type of soccer field, and so looking at the scene may not necessarily be may actually help the model to be able to perform, but that's really not what we're looking for. We're trying to associate the human action in the task with the we're trying to associate the human action with the video, not necessarily the background. Because of this, so simply collecting more data doesn't solve this problem. We can't just make UCF 101 a bigger data set, because in all the videos that we collect, most of these openly available videos of soccer are going to be in a soccer field. So like I said, we can't solve this by just collecting more data. And here, there's a couple of pie charts here that show the relative bias in a bunch of different data sets. So the blue is with object bias. So that would be like in UCF 101, the only class that contains a piano would be the class playing piano. So as long as the model can identify piano object in the image, then it doesn't have to even look at the person. And so the orange portion is scene. So that was, like I said, looking at for a soccer field or looking for the floor of a basketball stadium. And then people is the part that we actually care about. We'd like the model to be able to look at the people in the video to infer the action. And so there's a formal definition for bias, and it's essentially the log ratio of a model trained on scenes or a model trained on the representation versus a random model. So random model would be just picking the class completely at random. And then this by model trained on the representation, I'm referring to if we train a model on the scene. So if we train it to learn backgrounds, then how well can it perform on the data set? This gives us a quantitative measure for bias. So like I said, we can compare a random model and then a model that only uses scene in its feature extraction process. And so if that second model, if the one that uses scenes performs better than random, then we know that the data set has a bias. And you can think about this intuitively. If we look at the images in this picture, there's some type of gymnastics task in the lower left, and it looks like some type of ice skating in the lower right. And so the scene here correlates with the action being performed. As an example, we can go through the UCF 101, and then there's a bunch of other data sets that they measured. So they trained a model on the Places 365 data set. So this is a scene classification data set. And then they froze the weights of the feature extractor, and then they trained a classifier on the UCF 101 data set. So the features being extracted from the videos are only referred to the scenes. And this scene representation model that they had was able to score 60% accuracy on the UCF 101 data set. So that's pretty high. You would expect that if it was completely random, it would get 1 in 101 correct, which is about 1%. So it'd be 60 over 1, and you take a log of that as 4. And so UCF was actually the highest bias that they found in data sets. Some other common data sets, kinetics is another large one that has about 4, and then the diving 48, which we'll talk about later, actually was the data set specifically designed to have low bias. But I'll talk about that more later. So the authors proposed a solution to this. Essentially, they added two types of loss during the training of the model. They added, they call it scene adversarial loss, and that encourages scene invariant features. And so their feature extractor does not represent the scenes in its extraction. And then they added human mask confusion loss, which prevents the model from being able to predict the actions when humans are not visible. And so we can see the pipeline of this in the top straight across. It's you take the original video, do the feature extraction, they have their action classifier, and then there's cross-entropy loss. That's like the standard way to train a model. And then the two below that, they take the feature extractor, they do gradient reversal, which I'll cover a little bit more in a minute. But essentially that allows them to train an adversary in an end-to-end fashion, and that produces the adversary loss. And so this adversary is looking for scenes in the feature representation. And then in the bottom, there's a human masked video where they essentially hide the humans, pass it through the feature extractor, and then if the model is able to classify, then they induce a loss as well, because it shouldn't be able to classify when there's no humans visible. So some related works, there's been quite a bit of work in mitigating bias. Typically this is for demographic data, for age, gender, location, that type of thing. Over on the right, we have an example of it's colored MNIST. They took the MNIST data set and assigned a color, essentially the same color to each class, and then they tried to classify it with a test set that has colors from a different distribution. So you can see all the zeros in the train set are red, but then in the test set they're purple and yellow. So they want to be able to train a model that isn't tricked by that. There's also been work done in using scene context to actually improve the performance. A lot of times, especially in classic methods, being able to use the scene to look for things, especially things like salient edges around the object, can be helpful. And then other related works, just action recognition in video in general, and then video representation transfer for action understanding. Sorry, I tripped up on that. But that's essentially pre-training. So training a model on one data set, freezing the weights, and then training a classifier to have it perform well on another task or another data set. And then the most important related works here, there's adversarial training. So if you're not familiar, this is essentially, so an adversary is essentially another model or another method that they use to make the model, to make the original model more robust. So in this case, we have a picture of a panda, and our original model says that it's a panda with 60% confidence. An adversary generates some amount of noise, and then in the output image, the original model is now misclassifying it as a given. And so we would like that to not be the case. The human eye, those look very similar, and so it should be classifying it very similarly. And so using an adversary to generate this noise is a good way to make the model more robust to these small changes. And then lastly, artificial occlusion. So this is, again, another way to make models more robust, so they learn spatially distinct features. So for instance, in the top there's a picture of a fox. And so for a model trying to classify is this a fox or an airplane, if it's always looking for the ears of the fox, then in image, we want to be able to block out images we want to be able to block out the ears in some of the images. That way it learns features that don't associate with the ears. So that way it also looks at the snout or looks at other portions of it. And like I said, this makes the model more robust to when there's actual occlusions or other artifacts that would make it not able to use the features of the ears properly. So the authors, they used three types of loss when they trained their model. The first, like I mentioned, was cross-entropy. So this penalizes the model if it cannot predict the action correctly. So this is a standard pipeline for training neural network. We have the original video, it does feature extraction, and then they have an action classifier that works on the end of those features, and then they use cross-entropy to train it with the given label. The first type of loss that they added was scene adversarial loss. So this penalizes the model if it can predict the scene. So we want to be able to, since we're doing an action classification, we don't want to encode the scene in our feature representation. So you can't just have the model predict a scene and then punish it when it predicts it correctly, because then it would learn to just predict essentially a random scene. So what they do instead is they train an adversary. They take the same features that the model generates, and then the adversary is essentially looking through those features to try to find a scene representation. And if that adversary can find anything that encodes the scene in those features, then we're going to penalize the model for doing so. We would like it to not be able to encode the scene in its representation. And so the way that they do this is they use gradient reversal, which is essentially just multiplying the gradients of the model by -1 or some negative constant. And so that allows us to train end to end. So instead of generating the features and then classifying it with a classifier separately, or with the adversary separately, we can do it all in one step essentially. But the most important part of this is just to know that we're penalizing the model if it can predict the scene. And then the last loss that they add was human mask confusion loss. So this penalizes the model if it can predict actions where there are no humans visible. And so they just use a detector to find humans and mask them. They take a video, they mask away all the humans performing the action, and then they pass it through feature extractor. And then the same feature extractor that they used in the original video. And so if the action classifier is able to still classify properly, so if we can still determine what action when there's no humans visible, then we know that there's some type of background object or background scene being encoded, and so we want to penalize the model. We would like the model to only be able to predict if there are humans, because then we know that it's looking at the humans in the video. So this is that image blown up, and we can see all three stages again. There's the feature extractor cross-entropy, feature extractor gradient reversal adversary, and then there's the masked human video, or the human masked video, same feature extractor, same classifier, and then just the loss here, instead of using cross-entropy, we're using that loss to penalize it if it can detect the action. So this is the losses that they used. This is more just so when the slides get posted, if anyone was curious to see the actual equations they're trying to maximize and minimize. You'll notice that there's an argmax in there, and that's from the adversary versus the typical argument that we're used to saying. They're trying to minimize the loss for the cross entropy and for the human mass confusion. So to test their method, they used 3 different tasks. So they used action recognition, which poses the question, what action is being performed in this video? So there's an example of this in the upper right-hand side. We have a video, and then there's a video level label of swimming for that. Then there's kind of the next step up is temporal action localization. So this asks the question not only what action, but on what frames. So that you can think of this kind of like an untrimmed video, and then we're trimming it to the location of where the action is performing and telling you what action is being performed. And then the last one was spatiotemporal action localization. So this asks what action, what frames, and where in the frames. And so there's an example of this in the bottom right. You can think of this kind of like video detection or video object detection, except they're doing it for action. So there's a bounding box for every frame that the action occurs, and then there's also the class associated with it that says biking. So this is, you can think of it again like a long video. We're trimming it, when then we're saying this is the pixel locations in which the action occurs. So they had a few different data sets as well. So for the action recognition, they used a few data sets. There was the UCF 101, which I think everyone here should be familiar with, but the actions are broken up between sports, human object interaction, body motion, human-human interaction, and then playing musical instruments. And so you can kind of see why this has a relatively high scene bias when you see the actions, especially the sports is going to be where a lot of that kind of intuitively where a lot of that bias comes from, because a lot of the sports are going to be done in sports fields. But even body motion, a lot of the like gymnastics related classes are going to be in some type of gymnastics video. And then playing musical instruments, again, these are going to have quite a bit of bias because one, there's object bias from the instrument being in the scene, and then there's also the setting in which this is performed is going to be pretty distinct from some of the other classes. So for instance, surfing, you can look at the background and you can see that it's an ocean. There's the ocean versus something like applying eye makeup. There's probably some type of neutral background, or maybe like some type of like domestic, like a house setting. There's also, they tested it on the human motion database. So this has 51 action classes instead of 101. And this is facial actions and then body movements with some twists on those. But this one has a little bit less bias, but still quite a bit of bias. And a lot of that comes from the body movements class, because again, these are performed a lot in sports fields or like gymnastics settings. And so you can kind of cheat. Instead of looking at the human, you can look at the background in a lot of those cases. And then the last data set for action recognition was the diving 48 data set. So this is a set of, it's 48 classes and they're all diving moves. And so this data set was designed with the intention of having a low bias. And so all these actions, they're diving moves, they're all being performed in the same environment. They all have basically one human in the video. And so there's kind of no information that you can gain from the scene, since all of the scenes are going to be in a swimming pool. For the temporal action localization, they use the Thumos 14, which you can kind of think of like an untrimmed version of UCF 101. So in this one, they have long videos, and then they're trimming it to the location, or the trimming it to the frames. And you can see that here, there's the white bar, which represents all the frames, and then where it's highlighted blue tells you what frames the action is occurring on. And then for the spatiotemporal, they use the joint annotated human motion database. And there's a few examples of that here. You can kind of see that it's a subset of the human motion database, except in addition to just the video-wise labels, they also have bounding boxes for all the frames. And so I'm about to go through the actual quantitative results, but just note when we go through here, so the way they did this training is they trained on the mini kinetics, and then they froze the features, and then they trained a classifier on that. And so the standard method used just standard cross-entropy, and then they train the feature extract on the mini kinetics, and then they train the classifier on the other data sets. And also note that not all the results shown here are apples to apples. For computational resource reasons, the authors didn't test some of the bigger models with their method. They only tested the smaller ResNet 18 model. So some of the other ones outperform this model, but it's not necessarily a fair comparison. I'll talk about that as it comes up. So for action recognition, if we focus our attention to the bottom half of the table here, for all the data sets, the de-biased version of the 3D ResNet 18 outperformed the original ResNet 18. So for each of the data sets, it was like a 1 to 2 point improvement over the baseline. And then even compared to some of the bigger models, so the C3D backbone is about 2.5 times bigger than the ResNet 18 backbone, and yet the performance of the de-biased network is about the same as those. In some cases, it actually outperforms. For the temporal action localization, again, we'll focus our attention on the bottom part. There's the RC3D and then the de-biased RC3D. And again, for any of the IOU thresholds that they used, it improves the performance by a few points. And then it has comparable results to a lot of the other methods. However, the other methods did outperform the de-biased results. And then the spatiotemporal action localization, last time we'll look at the bottom half. There's the road data set and the de-biased, the road as their method, and then de-biased. And again, it outperformed by about 2 points. However, it was pretty significantly lagging behind the other two state-of-the-art methods. And then, so they also did, they looked at the results of comparing the relative improvement of their method versus the scene representation bias. So on the x-axis is the scene representation bias. So the farther to the right, the more biased the data set is. And we can see that UCF 101 is on the right-hand side because it's a relatively biased data set. And then diving 48 is on the left side because it has a bias of basically 1, which would be, and 1 being a completely unbiased data set. And then you'll notice the relative improvement decreases the more biased the data set is. So on the diving 48, they had a 15% relative improvement, and that's because their model didn't look for any of the background scenes when they pre-trained the weights. And so there was quite a big improvement on the diving 48 because it was focusing the attention of the model on the humans. And then in the diving 48, it could use that good feature extraction to classify well. However, on the UCF 101 data set, since it is biased, it actually might help to have the feature representations of the scene. And so the improvement was small, or actually may have made the performance worse. And then the last thing I'll go over here is it's a visualization technique. It's called class activation maps. And so essentially we are propagating the output back to the original image to see where the attention of the model is. So in this example, this was pulled, I believe, from the paper that created this method. We have, they're trying to classify dogs in images. And so we have a dog here, and then it traces it through the model, and then they add up the class activations, and you can see essentially it's a heat map of where the model is focusing. So we can see that the model is focusing very hard on the location of the dog here, and not so much on the rest of the image. And so they can use that to see, is their model actually forcing, or is their method actually forcing the model to focus more on the humans and away from the scenes? And so they show a few examples, and the answer to that is basically yes. So if we look here, so this is their method, you can see it's focused very intently on the human in the video versus the baseline, it's focused on the ground here. They might be trying to see, like, is this a basketball, or sorry, is this like a baseball field maybe? And then in this example here, the correct answer is javelin throw, and we can see that it's focusing on the person very intently again, versus in the baseline, it's focusing on the background of the track. And then the last one we'll go over here. In this one, it's balance beam, and it's focusing again very intently on the person, versus in the background here, it's focusing on kind of an interesting feature in the background. So the model, their method definitely is improving the attention of the model. So kind of to wrap everything up here, the authors of this paper developed a method for learning video representations while mitigating scene bias. So they're trying to train a CNN model to be able to perform action understanding tasks without using the scene representation. And they want to do this to be able to create more general models. So they created a couple loss functions to focus the model's attention on the human performing the action in the video. And by doing so, they improved on the baseline on several data sets and on several tasks. The only kind of downside to this method is that it falls behind state-of-the-art models since it was built upon relatively weak backbones. But potentially, given those stronger backbones, it could outperform. And in general, this was more importantly, this was a more general model and a better at transfer learning, so better at adapting to new domains or different tasks. And so that was all that I had for the presentation.